Welcome everyone to today's University of Texas Energy Symposium for September 2nd, 2025, the first of the fall 2025 semester. I'm Kerry King, Assistant Director at the Energy Institute and a research scientist here at the University of Texas. Before I introduce today's speaker, I will highlight upcoming talks. Next week, we will have Sanya Carley. She is the professor at the University of Pennsylvania, a distinguished professor of energy policy and city planning at the Weitzman School of Design. And she's going to talk about energy security and utility disconnection crisis in America. So a little bit of an energy and poverty, energy and utility costs perspective. The following week, we'll have Sheldon Landsberger from here at the University of Texas at Austin, professor in Department of Mechanical Engineering and study expert in nuclear engineering, and he will look at naturally occurring radioactive material in the oil and gas exploration field. Today is a pleasure to have with us Mark McClure. He's the co-founder and chief executive officer of the company ResFrac. Title of his talk today is Transformative: Improvements in Hydraulic Fracture Design, Applications for Oil, Gas, and Geothermal. So a little background on Mark. Started the company in 2015 to help operators maximize value through application of advanced geomechanics and reservoir simulation. Before founding the company, he was an assistant professor here at the University of Texas at Austin in our Department of Petroleum and Geosystems Engineering. He's earned his bachelor's, master's, and PhD from Stanford University. A little abstract on his talk. Widespread adoption of multistage fracturing in shale in the 2000s has been widely celebrated, of course, for unlocking enormous new hydrocarbon resources and transforming global energy industry. Less recognized since the mid-2010s is that hydraulic fracture designs have changed dramatically, resulting in large improvement in well performance relative to earlier generations. In many ways, the barrier to improvement was not technical, but conceptual, as Mark will explain to us. The mental model of hydraulic stimulation from shale in the 2000s has not proven to be representative of most of the shale wells, and it led to engineering decisions at the time that were suboptimal. And over the past few years, a similar shift has occurred in hydraulic stimulation designed for enhanced geothermal systems. So there are now large improvements being made in geothermal drilling for enhanced geothermal systems. So Mark will give us his perspective on the importance of critical thinking and evaluating the quality and confidence of the interpretations of incomplete information. What do we know what's going on underground, and how does it affect what we can do on the surface with the energy? And he will explain how his simulations and company have helped create this new understanding about hydraulic fracturing. So with that said, I will now pass it over to Mark. I will remind everyone to please submit your questions for Mark on the question and answer feature of Zoom, and we'll attempt to ask these at the end of the presentation. Submit your questions at any time. Thank you very much. And Mark, go ahead.
Well, Kerry, thank you very much for hosting today. It's very exciting to be here. As Kerry said, I was an assistant professor in petroleum engineering at UT for almost 3 years, and I can't say I was a weekly attendee, but I was a frequent attendee of this seminar. So it's fun to be participating today. So thanks everybody for joining. Also, I'm trying to talk about a technical topic today, but I don't want to be excessively technical. And so I'm going to try to assume that you don't know much about oil and gas. I'm going to assume you know a little bit, but assume you don't know too much, and also kind of, I think, tie this into a broader picture of, how do we as a community, a technical community, culturally think about innovation and change, and what are barriers that I think that I've seen in my career. So we're talking about these transformative improvements in hydraulic fracture design that have occurred over the past decade. And I say over the past decade, I don't say over the past 2 decades. So I'll skip ahead to this slide to give you the background. This is a slide I bet everybody's familiar with in some sense. This is United States production of crude oil over time. And as we see around 2010, a very large and what has persisted increase in oil production in the US. Multistage hydraulic fracturing has delivered that. And I believe everyone on this seminar is familiar with multistage hydraulic fracturing, going to shale formations, drilling horizontal wells, using zonal isolation to inject into sections of a lateral sequentially, making a large number of fractures. That has been the transformative technology that's allowed this really extraordinary increase in production to have occurred from from 20 years ago onward. But what I want to talk about today is I think a topic that's gotten a lot less attention and I think many people are unaware of, which is that the way that people did hydraulic fracturing back in 2008 and 2009, it looks quite different from the way it's done today. And that shift occurred around this period of 2015 to 2020 would be my sense. Um, it's still happening in some markets, in some places, but many of the things that used to feel very challenging to communicate in industry 7 years ago are now just the only thing anybody thinks. And I don't think a lot of people are aware of that and what's happened. And I think the why question I think is interesting. So I'm going to talk about that today as well as talk about how that relates to geothermal energy. I bet also everybody on this seminar, or most people on this seminar, are aware that significant improvements have been occurring in enhanced geothermal systems and the production of geothermal wells that have been hydraulically fractured. Those production rates have greatly improved just in the last few years. And again, I think it's a very analogous to what's happened in shale over the past decade, where a way of thinking and an approach to designing fracturing has been basically outperformed by a different way of thinking and a different way of performing of doing hydraulic fracturing. So that's what I'll talk about today. And at the very end, I'll give a little bit of perspective of, I've been right on the front row of this show and occasionally participating in it, and what it's been like and what I think it tells us about how we should be thinking about innovation and science as a community. So, yeah, so I wanted to start with some pictures. Here's me getting my PhD when I was at Stanford. Came straight over to University of Texas. So I defended my thesis in December of 2012, and I took a couple weeks off and we went to Mexico, but I spent most of the time on the beach with my laptop making my lecture slides for the class that I was teaching in the first week of January at UT. So got started at UT. This is the research group that I built up over a few years. It was a fantastic time, made a lot of great friends who I still really enjoy visiting. Um, but did have a little bit of a startup bug. So after about 2.5 years, I decided to leave. I left a year later. So I told everybody a year before I left and kind of completed my duties, and then founded company ResFrac. And today we're doing really well. So what we do in ResFrac, we design hydraulic fracturing treatments. So what I'm telling you about, of course, is what I know a lot about. We're a physical simulator. We simulate hydraulic fracture growth, proppant placement, uh, geomechanics of all these things, and then also production. And in fact, that's what we do kind of uniquely in the commercial market is we simulate all the reservoir simulation, multi-phase flow aspects, and also all of the geomechanics, fracture propagation aspects. Doing that in a fully coupled model is unique, at least commercially. Maybe not in academia, there are academic research codes that do that, but in terms of in the commercial market, it's unique, and that's really what we do. And it's been quite a ride. Won't give you the whole ResFrac story in this talk. But spent more than 2 years just developing the software. My co-founder, Charles Kang here, he joined about a year after I left UT. We commercialized it in 2018, and today we're really doing great. So there's more than 50 organizations using ResFrac. Of that 50, I bet 10 of those are academic institutions. We have a lot of academic users, including at University of Texas. Ton of papers, because I did come from academia. We write lots of papers. And I think this stat maybe really puts it into perspective more than anything. This all runs on the cloud, and there's 2.5 million hours of ResFrac simulations run per year, which is pretty radical to see that kind of growth. So really proud of what we've built. We have about a 30-person company today and still growing fast. But I think truly, a lot of what I did at ResFrac, or what I still do at ResFrac, is grounded in what I learned in grad school. And also then I came to UT, was very I think what made UT so special was it was such an outstanding research institution, but we had such a good tie to industry. And so talking to people in industry, hearing what people are working on, what data are they collecting, really helped me found this company, because what I found in running a company is you just listen to people, ask what they need, and then do the thing that they want. And so, I think UT was the perfect place for that, because I had so much opportunity to engage with the practitioners, make sure I wasn't too academic. And really, I think it was the perfect preparation for what became ResFrac. So that's my background. But I will be talking today about designing hydraulic fracture treatments, and I am doing that from the perspective of, I don't know the numbers, but I would say a pretty good percentage of the frac jobs in North America are informed in some way by ResFrac simulations at this point. I don't know. I wouldn't venture to put a number on it, but we really do a lot of engagement with industry, and so I do think I have my finger on the pulse of what's happening. All right, so back to the story that I'm going to tell you today. Again, to recap what I said a moment ago, around that 2005 to 2010 period is when hydraulic fracturing shale started taking off, and the gas production spiked earlier, and then oil production spiked as we got past about 2011, and that's been driven by multistage hydraulic fracturing in shale. So a key aspect is hydraulic fractures tend to form in a certain direction. If we drill perpendicular to that direction, we can create basically just stack a bunch of pancakes along the well. And so that's what we're seeing in this schematic here. Fracture, fracture, fracture. We can stack hundreds of fractures along a single horizontal well bore. That allows us to create a transformative amount of stimulation and produce from these very low permeability formations. But what I want to emphasize is what's different today than 2010, 2012. And I want to start with this figure here, which is an incredibly important figure. I saw this figure so much when I was in graduate school. It had a huge impact. This is from a paper by Fisher et al. In 2002. You may recognize a lot of the names on this co-author list, including our current, the head of the Department of Energy right now, Chris Wright, is the second author on this paper. It's an incredibly influential paper. And it's from the Barnett Shale, which was, of course, the first big shale play. And what we see here, it's a vertical well. That's the black dot. Of course, today, all the wells are horizontal, but very early on, they were not all horizontal. So they hydraulically fractured this well. They used microseismic imaging to see where the fractures are. And so what is microseismic imaging? What does that mean? When we inject water, we're cracking the rock, and that causes tiny little micro earthquakes. And if you put out an array of seismometers, you can do earthquake seismology on those little micro earthquakes, or we call them microseismic events. You can triangulate to where they came from, and then you can get an idea of where the fractures went. And so what they observed was typically what you might call a broad fairway of stimulation. So the width of this region of microseismicity is substantial. Just to kind of eyeball it, that's perhaps 1,000 feet wide region of fracturing from this vertical well. And so these turquoise lines here, they're not really measurements, but they're the interpretation of the authors, which is they've drawn these turquoise lines to represent the idea that they think there's a complex fracture network being stimulated by this injection. And the fractures are zigzagging all around in different directions, as you can see in this image. There's maybe some directionality. They've kind of created two sets here. But I really want to emphasize that they don't actually know that. What they have is a measurement of microseismicity, and they've interpreted that it created a complex fracture network. That concept of complex fracture network, that's the reason why stimulation works so well in shale, is something that was the conventional wisdom when I was a graduate student in the 2008 to 12 time period. And in fact, that was the topic of my own PhD thesis. I did, quote, discrete fracture network modeling, in which I tried to make fracture simulation models that looked somewhat like the cartoon, or this, the interpretation that we see in this image. But that's not what I do today, which is kind of remarkable. What changed, and why do we not really buy into this conceptual model anymore? Well, so first I should say that it's very perilous to generalize about things happening in the subsurface. So I'm going to make some generalizations in this presentation about what engineers in the industry think is happening most of the time. but I cannot promise that the generalizations that I make today are always true. And in fact, they are not always true. Uh, a complex fracture network looking like fracture network has surely occurred somewhere out there, from time to time. But what I would say is that with the benefit of hindsight, this does not look like most hydraulic fracturing in shale. And I would go further and I would say that this theory of fracturing actually held back progress. It was perhaps was progress when it was new, because that's how science works. We do our best to make the best theory we can at the time. But I think that it got too embedded and it took a while to get away from it. And I'll explain concretely how it impacted frac designs and literally led to inefficient designs and ultimately kind of loss of return on investment. So at the end of the day, we're engineers. We have to deliver things at, maximum revenue, minimum cost. Things that didn't do that were favored because of this theory. And I think that's where we need to be really careful to tell the difference between a theory and a fact. So what's the story there? So here's kind of more schematic of kind of people in industry kind of taking this complex fracture network concept and generalizing it. And again, I'm not being critical of this. In fact, this is what I was doing. I could go back and show you pictures of my own work from my PhD. They look like this. So this was the theory that was developed, that when you inject water, you're creating these volumetric kind of SRV, stimulated rock volume, this volumetric large region where there's lots and lots of fractures and they go in different directions and they kind of zigzag and they have this sort of pattern to it. This is something that was, I think, ubiquitously accepted, or nearly. I wouldn't say completely ubiquitously because it's not quite right, but most people bought into this. And here's how this impacted frac design. So, for example, most of these earlier shale wells use what's called an uncemented liner. So here's a schematic I pulled off somebody's LinkedIn post. He probably made this in PowerPoint or something, but it gets the idea across. So here we have this gray represents the liner, which is a steel casing. It's just a steel pipe that's running along the lateral of the well. So here we've drilled the well. We've got this horizontal section of well, and we've got a steel pipe going down it called the liner. And what we want to do is we don't want to inject, when we do hydraulic fracturing, let me take a step back, make sure you guys are all familiar with hydraulic fracturing. We're going to inject water at high pressure, and it is going to pop open the rock and propagate these opening mode fractures that rip down through the rock. Or we also might have fluid that goes into the natural fractures, the pre-existing fractures. And no question, there's lots of natural fractures down there in the ground. Some formations have more than others, but it's pretty uncommon for a formation to have none. There's always something down there. And so perhaps we are reactivating, causing deformation on those natural fractures as well. In conjunction with the water, we pump something called proppant, which is usually just sand. So you pump a slurry of water and sand into the ground. You can propagate these fractures. You place the proppant into them. So when you stop pumping, the fracture walls close onto the proppant, and they've created these highways of high permeability, propped fractures through the ground. And that's what's allowing oil and gas and geothermal heat to get into the fractures, into the well, and be produced. All right. So we don't want to inject just what we could call a bullheaded frac job. So a bullheaded frac job would mean, what if you just had a long section of well like that and you just pump a bunch of water and sand into it? What would happen if you did that? Well, water tends to take the path of least resistance. So let's say you've drilled a 2-mile long lateral and you pump a bunch of water and sand into it. You would make a few fractures. But you wouldn't make that many fractures, because after you made one fracture, maybe a few fractures, maybe a fracture every 1,000 feet or something, all the water and sand would just be going into that relatively small number of fractures. And we want to make as many fractures as we possibly can, because the fractures are these highways for flow that help us access the rock. And so that's why we do multiple stages. So multiple stages mean we might inject into just a couple 100 feet at the toe of the well, is the part that's furthest from the wellhead. So we might inject into the couple 100 feet at the toe. Then we might isolate, we might seal off that section of the well. We might move up the next 200 feet and repeat that process. And that's multi-stage fracturing. So the number of stages is the number of different sections you inject into sequentially. Um, in the 90s, they might, if they did a multi-stage frac job, it might be 3, 5 stages. Today, it might be 50 stages. It might be more than 50 stages. It might be even 100 stages in some wells. So the number of stages has gone up, up, up over time. But also, I want to look at what's happening. And the reason the number of stages has gone up, number one, the laterals have gotten longer. So a lateral, a horizontal well from 20 years ago could have been 500 or 1,000 feet long. Now it's could be 10 to 20,000 feet long. So the laterals are literally longer, and you can pack more stages into them. And number two, I think the stages have gotten somewhat shorter. Um, Although I think we've kind of gotten into this 150 to 350 foot range is pretty much where I'd say 90% of things are. Um, so within the stage, how do we deliver the fluid and the sand to the rock? And that's what I'm showing here. So this gray feature here is the liner, and it's steel pipe. So fluid and sand cannot flow out of steel, obviously. But we need to get it out of the pipe, so we have these flow ports, and there's different ways to do that. Generally, like a ball drop, and I won't go into the details, but you can believe me that there's basically openings that we can make in the steel pipe that allow the water and the sand to get out of the steel pipe. Um, Now, the steel pipe is smaller than the well bore. So we're going to drill a well bore of a certain diameter, and we're going to run a smaller diameter pipe into that well bore. And so they would accomplish isolation with what's called a swellable packer. So that means outside of the steel is an annulus. We're going to swell up and we're going to seal the annulus. That annulus is, in what I'm showing here, uncemented. So the alternative is we could pump cement and we could cement the annulus, so we seal the steel pipe in place. But they usually didn't do that. Now they did sometimes, but many or most of the frac jobs of 20 years ago were uncemented liners. And so what they would do is they would inject out of these flow ports. They would have several hundred feet of uncemented kind of open hole around the casing, and then we would have these swellable packers. So the question is, kind of what happens once the fluid gets out of the flow ports into this annulus, and then it's contacting the rock? Well, one of the reasons why they didn't want to cement the annulus was because it would maximize contact with the natural fractures. So going back to these ideas that, wow, the natural fractures are so important. That's what creates the quote complexity that's so valuable. That's what's going to create these broad regions with lots of fractures that are stimulated. So we want to access them as much as possible. And so that would motivate you to not cement this annulus. And the idea would be you'd not cement this annulus, and you're just going to get tons and tons of fractures that are forming or propagating or stimulating off of this annular region, and we're going to get these great regions that don't look like we're modeling here of these volumetric clouds. So that was the concept, is to use uncemented liner. I would tell you today, this is, at least in US, very rare in shale. So I just articulated why you would do this, and they did do it, and it's not a terrible idea, but there's a better approach, and so we'll explain why. It's because when we have this discrete fracture network, this complexity concept, it was really focused on stimulating the natural fractures. And so number one, that tended to downgrade the importance of proppant to people. There was an idea that, well, the natural fractures will hold themselves open, and we don't need to pump a lot of sand because they're self-propping was the term. There's even a cute named paper that said proppants. We don't need no stinking proppants. And again, there's somewhere in the world, there's a formation out there that someone could find in their long career where you didn't need much proppant or you didn't need proppant. However, what I can tell you is that in the industry over the past decade, in every shale play, proppant volumes have dramatically increased. And it's because if you pump more proppant, you get a lot more production. And so that's one of the ways that this DFN model, I think, slowed people down, is people were very hesitant and conservative about going up, 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 up on proppant volumes because they just conceptually didn't think it was necessary. And I'd love to say that it was the physics-based scientists who figured out that we needed more proppant, but it wasn't. It was just people pumping more proppant and observing they got more production. I think that's really the crux of what happened. And it was actually the physics-based people who had the wrong idea and were perhaps inhibiting the correct idea, which I think is a lesson for us. Um, the other thing is that we don't use these uncemented liners anymore. In fact, now we always cement the annulus, which is counterintuitive if you think that maximizing contact with natural fractures is important, because there are a bunch of natural fractures. And if you cement the annulus, that means you've placed cement between the pipe and the rock. You can't pump into those natural fractures. Nevertheless, it results in much better production if we cement the annulus. And it's counter to the conceptual model. And that gets around to another very important concept that today is uncontroversial in the industry, but was not obvious to people. I mean, it was known, it's been around for a long time, but it wasn't really core to shale engineering yet. And that is what we call limited entry completion. So with limited entry completion, this is done with a cemented liner. So we're going to put cement around the liner. And then we're going to do what's called plug and perf. And so we're going to use explosive charges called perforation guns to make holes in the steel pipe, and we can decide where to put those holes. And why is that valuable? Because we can control where the fractures form and where they initiate. And so if we leave this annulus uncemented, we pump into the annulus, and then fractures could form wherever they want to form. And the hope was that they want to form a lot of places and will make tons of fractures. It turns out that if you leave the annulus uncemented, you're probably going to make about one fracture. And it doesn't matter if it's a 600-foot stage length or a 200 stage length, you're making about one fracture. And maybe you made two fractures. That's really not great. What we do with modern high density fracturing with plug and perf cemented liner is we actually can put a fracture every 20 feet. And how do we do that? Well, you've got a cemented liner, and then you're going to make these perforation holes in the pipe every 20 feet. And now it's not necessarily easy to make a fracture every 20 feet, because what happens is once you start pumping into one fracture, it strains the rock and it compresses the rock around it. And that rock will increase stress, and that inhibits the neighboring fractures from propagating. In fact, that's why when you have an uncemented liner, you make one or two fractures because of so-called stress shadowing. But the really clever engineering solution that, again, it's decades old in the industry, but which really got really broad adoption in oil and gas a little bit later in the shale, broad adoption in shale a little bit later, is called limited entry. So the idea is that, let's say you're pumping 90 barrels a minute at the surface. Well, that's like a couple of fire hydrants. You can't put 90 barrels a minute down, a tiny little perforation hole in a pipe that's this big. It's 0.4 inches in diameter. And so they actually restrict the number of holes made along the pipe within the section so that the flow rate per perforation shot, in other words, the number of places where fluid is literally flowing out of a hole in the pipe, there's not that many. And as a result, there's kind of a throttling effect that happens there. It's kind of like a nozzle, and it requires meaningful delta P to push fluid across each one of these perforation shots. And that delta P scales with the square of the flow rate. And as a consequence of that, that forces fluid to exit the well in a uniform way. Because if you pumped this open hole thing, you might be able to get 45, 90 barrels a minute into a single fracture, actually. It'll open up a lot. But if you are trying to put that down a single little hole in a pipe, you just won't be able to do it. So limiting the number of holes in the pipe and then placing those holes at the spacing that we want allows us to basically place a fracture every 20 feet along the lateral. And that's a lot better than placing a fracture every 200 feet or every 400 feet along the lateral, because creating fractures is everything. Now, what about the natural fractures? Well, what about the natural fractures? And so I'll just show here, I just got some slides here showing that, yes, in fact, wells produce a lot more than they used to. And that's because of the adoption of high density plug and perf fracturing with cemented liners and larger injection volumes of proppant and sand. And so I think it's quite clear. This slide here is showing the stage length dropping over time, the cluster spacing dropping over time, the injection volumes increasing over time, and that going directly into increases in production. So, what do the fractures really look like? Well, I'm going to show you. This is a paper that we wrote in the Eagleford. This was actually a Refrac optimization study. So we did this with Chesapeake in the Eagleford. The work was done in 2019, 2020 time period. And we simulated a well that they had been producing for 3.5 years. And down here, you can see images of this simulation. So this simulation is a single stage, or maybe it's a couple of stages, so it's not the full well. Number two, the fractures are actually very close together. If you look at this in pure dimension, we've stretched the image to make it easier to see the fractures. So the fractures are in fact closer together than this. But what we did is we took that well that had been fractured 3.5 years prior, and we did a history match. We simulated the data of the fracturing, simulated the data of the production, and then we showed that, hey, we built a model that is consistent with all of the data. And then we said, all right, what if you do a refrac? So what's a refrac? Well, a refrac means we're going to take an old well and we're going to fracture it again. And there's a few different ways of doing refracs, but the most common is to basically redo the frac job with tighter perforation spacing. So this job here that had been done prior, they had put the perforations pretty far apart. And I don't remember the numbers. Let me just make up a number for the sake of discussion. Let's say the perforations were 100 feet apart. So we said, all right, well, we think you made one planar fracture every 100 feet. And guess what? We matched the data. We matched all of the available data. We did not need to invoke anything about a complex fracture network. In fact, quite the opposite. If we had done that, it would have made it harder to match the data. And then we said, all right, you're going to come in and you're going to do a new frac job. What they actually do is they put a new steel pipe inside of the old steel pipe and they cement it into place. So there's actually an inner pipe, an inner annulus. They cement all of that together, and then they do a plug and perf. And instead of putting the fractures every 100 feet, every 200 feet, they're going to put the fractures in the perf clusters every 20 feet. And so we said, we think you're going to go in and do that. We simulate the physics of the stress shadowing and the perforation pressure drop, and we do all of that, and we simulate production. And we said, all right, this is what we think the fractures used to look like. This is what we think the fractures look like now. And here's what we think the production is going to be. So what was fun about this paper is they came back 3 years later and they said, hey, you want to see how you did? And this is how we did, right? So the dashed line is the actual, the solid line is the simulated, and we did pretty darn well. We were very good on predicting how much new production you'd get. But I think that these images make it really clear why the older style designs weren't working, because they didn't make a complex fracture network. We can always, I mean, literally always match the data with a simple planar fracture at every perf cluster, and it's fine. And then you come in with a higher density stimulation, you do get more production. So this is why refracs work. We have another paper we did this year with other operators on refrac. This was a blind test. So they gave us all the data prior to the refrac, but they didn't tell us about what the refrac did. And we predicted how much uplift there would be. And then this is a cross plot of the prediction versus the actual. What you see is we predicted it really well, but also there's a big spread in the performance. So these dots out here represent, so this refrac uplift is in the first year after the refrac, what percentage of all prior production did they get? So these two dots had been producing for many years. And in 1 year post refrac, they got 50% of that production back. In the long run, this is a well where the production is going to 2-3x because of the refrac. So what differentiates the well with small or large uplift? It's the intensity of the prior frac. So fracs that were already done with a perf cluster every 20 feet and a cemented liner, those don't see good uplift from doing a refrac. The ones that were simulated with much wider fracture spacing, they do see an uplift. And so just empirically, we see this thing where we had this idea that we shouldn't pump much proppant, we need to use uncemented liner, and it took us 180 in the wrong direction. Actually, yes, there are natural fractures, and they might contribute to production. They likely do contribute to production. However, were they really the most important thing? They weren't. Actually, the fracture geometry is not as complex as we thought. And so now let me get to that statement. What do the fractures really look like? And here's some more examples of a pre-refrac and a post-refrac, which is accurately predicting production and matching all data, showing how these early stage designs that were hoping for complexity, they didn't get it. We don't need to invoke it to match any of the data. And if we in fact assume it's not there, we match the data really well. But then I think, how do we get to an idea of what the fractures look like? And I think that's kind of the revolution that's happened here with new data. So around 2015-ish, mid 2010s, new sources of data became available. And I think the most important and most valuable has been fiber optic. And so you can place a fiber optic cable into one of these laterals. And what the fiber optic cable does is if it's deformed as it stretches or contracts, it can measure when and where that deformation is occurring. And so we can see that, I'll show you some pictures right here. So this is what we call a waterfall plot. On the x-axis is time, and on the y-axis is distance along the lateral. The red is tension and the blue is compression in this image. So this heart of tension, that's happening because there's an opening mode fracture propagating through the rock and approaching this well. And that heart shape is predicted by the fracture mechanics theory, and we see the heart shape all the time. It's really cool. The minute the crack tip crosses the well, then it flips. And now instead of seeing tension ahead of the crack tip, we see compression along the sides of the crack tip. So these sorts of measurements are now ubiquitous in the oil and gas industry. And it happens because when they drill these pads, they drill a bunch of wells that are all alongside each other. So you could easily put fiber into a couple of these wells, and when you fracture this well, you can see where the frac hits occur. So where the fractures are, what they look like, you can see them at different spacings, different well distances. We get a really good idea of what the fractures look like, what their orientation is, where they're going. Um, and what they generally see, not always, but I'd say a large majority of the case, what they see is called a frac corridor. In other words, if you pump a 200-foot stage length and you draw a straight line in the direction the fractures are supposed to be going, there's going to be a 200-foot region where you see the frac hits. That's completely different from what we saw in the Fisher paper, but that's seen over and over again. Not every time, but very, very often. So here's a great paper, Gustavo Ugueto from Shale and many others were writing this paper. This is a paper from Apache where they're showing something similar. And so the difference is that these fiber observations, they're pretty much direct measurements. In other words, there's really not a lot of ambiguity. There's nothing else that could happen that could cause something like a frac hit signature in a fiber optic. It's pretty precise and pretty accurate. Um, I think what's happened with microseismic is sometimes there's location uncertainty. So it's actually a very complex and non-unique process to figure out where these microseismic hypercenters are. And it seems like it overestimates uncertainty in many cases. Not always, but sometimes. Also, I've been on many projects where we had the opportunity to compare microseismic with fiber. And sometimes the microseismic is quite good at predicting when those frac hits are going to be seen in the fiber. I have also seen cases where it was not. In fact, I would say generally fiber tends to see longer fractures. Earlier in my career, I was actually very bothered by how short the fractures seemed to be because all I had was microseismic. And it was a big problem. I was even writing papers about how do we explain why fractures are so short. Um, it turns out that the minute we got the fiber, the fractures got a lot longer. And it's not because anything changed other than we got better data, basically. So the fiber has been really, really valuable. We use microseismic a lot, but I think what we've seen is that there was an underestimation of error from microseismic, and there was a systemic failure to cross-check microseismic observations and interpretations to make sure that they were definitely correct. And I think in many cases they were imprecise and they overestimated the width of fracturing, and they were also inaccurate. They have sometimes missed the length of fracturing. And I think it's just a lesson that when we have I think there's a tendency with things like remote imaging to not cross-check with hard measurements and make sure that interpretations are correct. Instead, interpretations are presented as fact or measurement when they are not. So I think that this fiber has been revolutionary and given us incredible detail that we didn't have before and confidence we didn't have before. Now, the picture is complicated because there have also been core-through studies where people actually drilled wells through the rock and excavated cylinders to see what the fractures look like. And they've been surprising in both respects. So first of all, they don't look like zigzagging fracture networks. So fracture orientations do not look like shown in this image. They have not looked zigzaggy or unpredictable. They've tended to be quite consistent in the core through studies. What's surprised in the core through studies has been often they're multi-stranded. So this image here, that's a 1 foot length scale. So 1, 2, 3, 4, 5. That's 6 fractures across 2 feet. That is a huge surprise. Nobody expected that. Um, Actually, it's been observed in a lot of prior core through studies prior to the 2000s, but I think what changed is um, it kept happening. People kept doing core through studies and kept seeing this. I don't know of anywhere it hasn't been seen, actually. So the mental model that I'm working off today is I do think the fractures are quite consistently oriented, but I think at small scale, what we're calling a fracture might be a swarm of fractures. It does have some smaller scale complexity. So it's certainly a complicated story. But yeah, the phrase that I use is complex at small scale, but relatively planar at field scale. That's really different from what I learned in grad school. But hey, we took the stuff out of the ground and we looked at it. It's hard to argue with that. There's other types of measurements. So, for example, Exxon and Hess have recently published studies where they drilled wells and they never fractured them. They put in fiber, but they also put in pressure measurement gauges all along these laterals. So now we can even measure what the pressure is far field. So we frac, we produce, we say, hey, well, when we're producing, what is the pressure 500 feet away? And how far did the proppant go? And direct measurement is much more expensive, but even a small number of direct measurement studies can be much more impactful because they give high confidence answers. And often, when we deal with low confidence answers, we're really just guessing and we don't actually move the ball down the field very much. All right, so that's what's happened in Shale, and I got to watch the clock here. I want to leave time for questions. Very briefly, I want to say this is also analogous to something that's happened in enhanced geothermal systems. So this is a plot of flow rate from enhanced geothermal systems wells. So the idea here, we're going to go to places that are hot but low permeability, and we're going to fracture wells. We're going to connect them, and we're going to circulate fluid between wells. And as fluid goes from injectors to producers, it heats up. We can produce that hot water and generate electricity or use it for direct use. So flow rate is everything. The more flow rate equals the more dollars you can pay for the project. You can lower the cost per kilowatt hour. One thing is people have gotten a lot better at drilling geothermal wells in the last few years, and that's a great story. But the story I'll tell is they've also gotten a lot better at fractured wells. So these bars represent the flow rate achieved at different historic EGS projects from the 70s through the 2020s. And these are really the best. There's a lot more, and these are probably the best EGS projects out of dozens, maybe 50 or so, I'd bet. Fervo Energy is a really neat startup. We're proud to work with them here in ResFrac. Their first ever field scale project, they doubled the best ever record. And then the next one, they did another 50% increase on top of that. So, how did Fervo go to a field that's 50 years old and instantly start dominating all prior results? That's literally what happened with these frac designs. And they've been very, successful. They've been raising a lot of money. They've grown a lot. They have a lot of ambition. Just awesome to see what Furrow's doing, and I couldn't be more excited and proud of them. And I'm proud of them because ResFrac ourselves, we've been helping them design these frac jobs for many years, even before they had a company. They were ResFrac simulation results in their pitch deck. So we're really proud of that. And really what we've done is just taken these same cemented liner, limited entry plug and perf concepts, these concepts that have been so effective over the past decade in oil and gas shale, and just say, hey, that's going to work in geothermal too. And you might ask, why haven't people been doing that? And it's a kind of similar story. In the 70s and 80s, especially the 80s to 90s, the concept of stimulating a network of natural fractures became very strong in the enhanced geothermal systems community. And so, similarly, the design decisions were being made. Companies would not use proppant. Um, they were not willing to use cemented liners. In fact, they struggle with open hole packers at these temperatures and these wellbore diameters. So people weren't even using multiple stages. So the improvement has happened because we've gone from proppant-free, bullheaded, single-stage stimulations to high-density fracturing with proppant and multi-stage wells. And that's just a total 180. But it's actually the conceptual idea that people had that we were going to create this stimulated natural fracture network that slowed progress in EGS because it gave people a rationale for doing frac designs that actually were really, really suboptimal. And if I went to an oil and gas client and I said, "Hey, I think we should drill a vertical well and bullhead a bunch of water in your next, Bakken well," I wouldn't have a job for very long. But that's what happened in EGS for many decades because of this concept around stimulated natural fractures. It was insightful when it came out, and there's a lot of kernels of truth to why that concept came out. But some of the work I did in my PhD when I was at UT, wrote this paper here with my former advisor Roland Horn. We went back and we looked at a lot of data, and I won't go through the whole story, but we said, hey, actually, we think that every single EGS project in the books, all of them did hydraulic fracturing. All of them made new fractures, and the data is pretty clear on that. But when people are looking for something else, then they can find it. And I think there's a big tendency in subsurface engineering to kind of see what you're looking for. And I think that happened in shale, and I think it's happened in EGS. So yeah, the shear stimulation hypothesis led to ineffective frac designs. A review of the data would suggest that in many or probably the majority of EGS projects, shear stimulating natural fractures has been ineffective. Not to say it's never been effective, it is effective in some situations, but it largely has led to suboptimal frac designs, and that's the shift in thinking has motivated the shift in frac design, which has led to the successful changes and improvements. All right. So I will kind of just give a recap on some of what I see as these challenges. These are just a few examples in my career of what I would perceive as there's kind of a hypothesis or an initial interpretation of something that becomes adopted, and then it becomes very difficult to dislodge something once it's taken hold. I think a lot of really good scientists and engineers are capable of ignoring obvious things in hindsight. There's a lot of confirmation bias out there, and it's just human nature, right? In fact, the widespreadness of a belief is itself seen as proof of the belief's validity, which I think is backwards, right? Um, very specifically, what I observe is, I'm in modeling. It's very common for people to write modeling papers in which the model gives a result and then they present that result as fact. In fact, it is not. It is a modeling result. There's a tendency in geophysics to do an interpretation of remote imaging and present the interpretation as fact. And in fact, it is not. It is remote imaging. So I think that people, both in modeling and in many other fields, we tend to overestimate our confidence in an author's interpretation of ambiguous data and uncertain data. And I think one solution is to really lean hard on gathering direct measurements, the core through studies, the fibers that literally measure strain at a physical location with a well. Those are concrete and they really move the ball down the field in the way that we can't now. We can't always afford direct observations. Often remote imaging and modeling is cheaper. But what we need to do is we need to do the cheap things that are accessible, and we need to constantly cross-check them with the expensive things that are definitely right or very likely right. And I think that often we short circuit that. Also, I was in academia. I still write papers. In my personal experience, whenever I've had my best work, those have been the hardest papers to publish. Um, when I think I see something that is important for people to hear, it's hard to get the message across. It's hard to get listened to. I would even say, in terms of, I never went up for tenure. I left after 3 years, so tenure never came up, and I'm confident I would have gotten tenure. I think I was doing well, but it was going to be scary because there were cases in my short academic career where I pretty much disagreed with prominent people in my field, and I did know that they were going to send out letters to people and ask for recommendations for my tenure someday, and it is scary. I mean, I think that the system of academia is all around making everybody like you, and what I found is that questioning a common belief is not a good way to accomplish that. So I think it's just there's structural challenges there. I think the group of people that I've found who are most interested in and open-minded is surprisingly now, but it's the operators. It's the oil and gas companies because they actually have to go out, and if they frack a well and they get more production, they get a direct feedback that tells them this was the best thing to do. And if their neighbors get better production and they don't, then they are going to be impacted by the market. And so they are more incentivized than anybody to get the right answer. And I found that that's why I've really enjoyed working with operators and found them to be, I'm generalizing obviously, but operators are fun to work with because they're really truly their incentives are aligned with getting the right answer in a way that surprisingly isn't always the case, I think, in academia or with service companies. Um, Many historical examples. Bloodletting and radical mastectomies are two examples. This is a fun paper I found a couple of years ago about this. But there are countless historical examples of beliefs that continued to can be in practice among people far after they were disproven. So finally, kind of how do I think about addressing this sort of thing? I think talking about challenges is number one. So in ResFrac, in our company, we have culture and values meetings where we talk through things like this. To do good engineering, you can't be too kind of ego vested in something. You have to be willing to say no. You have to be able to have a disagreement. So if we have an engineering discussion, I think one thing, you think something else, we need to be able to just openly express our opinions. We can't get our feelings hurt. We can't be judgmental if we think someone's wrong. We can't be embarrassed, or we can't be, we have to be aware of these problems. And my view is, if you talk about this and you're aware of it, then that diffuses it to a large degree. Um, I think what's surprising is how rarely this gets talked about. And another point I'd make is it what I'm saying is very counterintuitive to kind of normal human interaction. So, if you're with a group of friends and you're deciding, where to go to dinner, and you don't agree, then, you're just gonna have to go along with the group, right? And that's just how people should be. But when we are engineers or professionals and we have an obligation to get the right answer and do our best to get the right answer. And seeking consensus and agreeableness is actually a recipe for disaster when we really have a responsibility to get the right answer. And I think, again, the key to that is we just try to talk about it. We just try to raise this, make sure everyone's aware, it's in the back of your mind, so that the next time this comes up, you're kind of armed. And culturally, everyone knows that we have the norm that it's okay to disagree and that we're going to try and get the right answer. So to me, I think that's a solution, and I think that should be done more in all the technical fields. I don't think we talk enough about this in the technical fields, and I just think I think that could help a lot. So I'll pause there. I've gone a little too long, but I've left some time for questions.
All right, thank you, Mark. Yeah, we could definitely talk to you further about whether there are some paradigms and sciences or social or physical sciences that have seen their time, but for a future discussion. So we got a few questions here. So I'll just kind of go through them a little bit. So were there innovations necessary in the fracking fluid chemistry to support kind of the physical aspects that were happening, or and did you have to think about those in your simulations, or how do we think about that?
Yeah, well, the trends in frac fluids have largely been to simplify the frac fluids, actually. So, you've heard of slick water fracturing. You've probably heard of that. So one type of you can basically choose the viscosity of the fluid. You can pump a very, very thick fluid or a very lower viscosity fluid. And the lower viscosity fluids have become wider spread. And there's a healthy debate on why that is. But I think in many ways it's been to simplify things, and try to kind of do no harm. I'll give you a great example. In the scoop stack in Oklahoma, there's a tendency for the polyacrylamide frac friction reducers to actually cross-link with a very iron-rich formation, and they actually can gunk up the fracs. And so you actually can really harm production by pumping a frac fluid that's not the right frac fluid. And so big innovations have happened there. This is hardly published at all, but by just doing work on testing different friction reducers and their compatibility with the formation in the scoop stack has really helped a lot production there. So I think it's things like that. It's been simplifying down. It's been going to lower viscosity and frankly cheaper. So cost is a really big issue here. So people are just trying to go to cheap, but then you don't want to have bad interactions with the formation. So yeah, there's another concept called high viscosity friction reducer where you can use this polyacrylamide friction reducers at higher concentration. That's used sometimes, but surprisingly, it's been the thin simple fluids that have been mostly used to date. But yeah, compatibility with the formation is incredibly important.
All right. Yeah, you showed this kind of classic one of the slides here, layout of different wells and the fractures, little yeah, this one kind of here. So you gave some geometries. Someone's just kind of asking to give a little of the geometry XYZ if you can for us.
Yeah.
The laterals are so long. How close are they together? Each lateral, this kind of thing.
Yeah. Well, depths are probably 5 to 15,000 feet deep, with 10,000 being the most common. These days, laterals are from 10 to 20,000 feet long, so that's 2 to 4 miles long. Well spacing, well, it's both lateral and vertical. So if you have formation in the same formation, you could see 400, maybe even 350 to 1200 foot spacing laterally, vertically, any amount of spacing. So often the formations are very thick, and so they're wine racking. They might have a lot of different landing zones that they're hitting. Um, but yeah, I hope that kind of helps give some. In terms of what the fracture sizes are, fracture lengths and heights vary a lot, but fractures could propagate maybe 1,500 feet. Sometimes they might propagate 4,000 feet laterally. They might be confined within a 150-foot zone. They might go up. I've seen a project unambiguously for sure. They went up 1,800 feet. That was very unusual, but that's kind of the extreme end of it. So hopefully that helps.
Right, that helps. As a question, a little bit of terminology here, but that you know. Do you believe small scale complexity in quotes around fractures promotes production, or are you able to match mostly when you do your modeling? Are you able to match the production or what you think the fractures are with matrix permeability and simple planar fractures? I think that's
We
mostly
have always been able to match it with simple planar fractures. I've never had a project where we needed complexity.
There you go.
And I think that actually gets into a deep question, which is what is the permeability? So, the permeability is how easily can fluid flow through the rock. And if you think the permeability is very, very low, then you will naturally think that there's more fracture surface area. If you think it's very high, you'll have the opposite. And what's incredible is there's about 100,000 X difference in low and high permeability estimates that I've received in the same formation. So I could find you a paper from Barry and Miskimmins where they say that the fracture effective lengths are 30 feet, right? They have a planar fracture that's 30 foot long. And they think that's because they think the permeability is too high. I think that they were wrong. They used the wrong permeability in that paper. Conversely, we can go back to other studies where people are using very, very low permeabilities. And so that could lead to some differences. The way that we get permeability is called a diagnostic fracture injection test. So you pump a small volume of fluid, you monitor pressure over time, and based on how quickly the fluid pressure dissipates, you can go back calculate kind of what the permeability has to be. And I think that's a good way to do it because you're really looking at flow through the formation. And if there's fractures, you're getting all that. So we take those defit perms, we put them into the model. It works.
All right. Here's one a little bit on the kind of fiber optics. Someone saying they understand the improvement and being able to measure results where the fractures are and these pressure changes. Do you think what are the blind spots of using fiber optics? What do you know, or do you know what you're missing in terms of other information you want to know that's not giving you? It sounds like that was quite an improvement in resolution and understanding what's going on. So just wondering what's next. Yeah.
Yeah, well, I am crazy about this. To see where frac hits occur, to see when they occur, even things like orientation. So if the fracture is in fact curving off at a 45-degree angle, you can infer that as well. I love that so much. It's so valuable, both for enhanced geothermal systems and for shale. It just collapses so much of the uncertainty. And I really do think that that is pretty darn reliable. I mean, there's some challenge to precision depending on the type of fiber that's used. One of the next frontiers there is they're even trying to see where production is happening. So when you start drawing down, you can see a little bit of a contraction. So that's really exciting. I think the next challenge for us, we're really working on where's the proppant go. So I said the fracture could go 4,000 feet. The proppant does not go 4,000 feet. The proppant might go anywhere from 20 to 50% of the fracture length. And so here in this project, Exxon did a great job of that. They have a slanted well so they can monitor pressure at different distances. And they're saying, hey, we got to a certain distance and all of a sudden there was no more depletion. Even though we know for a fact the fractures went a lot further than that. So that's how they're inferring what the propped length is. We still, we have ways of estimating the propped length, but that's still something that's too difficult and very important, I'd say. Our conceptual model right now is that we're getting almost all the production from where the proppant is.
Right. Here's a question on the geothermal side, saying with a 20 or 25 foot cluster spacing, enhanced geothermal wells, can be shown to achieve nearly 100% heat sweep efficiency. You can discuss that if you'd like. Even if all the fluid flow is strictly in the propped fracture, so I guess that means it's only going in where you think you fractured it. I don't see many people taking advantage of this for stimulating heat flow with no need to resolve the rock between the fractures. So what are your thoughts on this? And maybe you could mention how close like an injection versus an extraction well are for enhanced geothermal as well.
Yeah, so enhanced geothermal, the spacing of the wells that have been published to date has been pretty tight. It's been like 350 to 500 feet. In fact, at the Forge project, they were even closer. Um, you'd like to put those wells as far apart as you can because the more rock there is, the more heat there is to extract and the longer they'll last. And we know we can make big fractures, but it goes back to proppant. So how far can we get the proppant out and connect fractures? And I think that's TBD. I think we'll probably, like Fervo, I think over the next few years, they have a bunch of wells that are at somewhat different well spacings. And at some point, they will have tested all of them, and then we'll get back data on kind of what's the flow rate as a function of well spacing. We're going to learn more how to optimize that. I think that heat sweep efficiencies have the potential to be good, certainly not 100% nor 50%. Um, but I think it's important to us to do everything we can to engineer to maximize our heat sweep efficiency. It all comes down to uniformity of flow. So we're going to create all these propped fractures. We want the flow per fracture to be as high, as similar as possible. So we don't kind of cool down some places more than others. And we want to place these fractures as ubiquitously as possible. I think that publications to date have been very encouraging on that uniformity of flow topic, but I don't think we need to take that for granted. And I view this as one of the most important areas for R&D is to try and improve the repeatability and confidence that we can have a uniform, closely spaced fracture network every single time.
Great. Let's here's one. It's frac measurement, perhaps using the optic fiber cables or other kinds of techniques. It's its own specialty with firms. Does ResFrac do this kind of measurement, or do you just use it, or is this done by the operators, and or has this changed over time? At first, it's specialty firms, and then now it becomes more easily done by the operators.
Yeah, so for fiber optic, I mean, ResFrac, we're just a modeling company. So we just take whatever data people have and we ingest it. So we have become opinionated about what kind of data we like. So that we have a perspective there. Um, but no, we don't even interpret it. We prefer for the service company to interpret it. Yeah, originally it was only some more specialty firms. And there are still great specialists. So like Nubrix does a great job. Silixa is a great fiber company. But these days, yes, you could go to Halliburton, you can go to the mainline service companies, and they will also do this sort of fiber optic work as well.
Right. There's another one. There's lots of questions for you this time. Are there physiochemical parameters you need to know better to, I guess, yeah, understand the fracturing or simulations, and you could maybe interpret that for us a little
Yeah,
bit.
I think that, I think chemical effects, there's tremendous opportunity to improve our understanding in that area. First, let's start with EGS. Every geothermal system is going to be different, and most of them are going to have some kind of chemical problem or another. At the Forge site, they've seen evidence of calcite scaling happening. The water being near saturated with calcite. And we certainly do not want to have mineralization clogging off these flow pathways in the long term. So chemical effects are going to be very, very important to study and optimize from an EGS perspective. In oil and gas, shale, I happen to think it's more important than probably most people think. In our work, we pretty strongly believe that over time, the proppant pack conductivity, its capacity for flow is choking off. And I think there's great evidence to suggest that a lot of that is happening because of chemical effects. So, an operator saying, "Hey, I've got a bunch of calcite depositing in my pipe." Well, if it's depositing in the pipe, it's probably depositing in the proppant pack, and it's clogging up those flow pathways. So, I think there's a lot of indication for chemical effects over long-term production, degrading production. Certainly in the frac fluid part of it, also in frac hits. So when newer wells called child wells are fractured, their frac fluid goes into the older fractures. And in some places like the Montney or the Scoop Stack, there's often a very severe loss of production, which appears to be driven by chemical negative chemical interactions with the frac fluid and the what's in the producing fracture. Um, so a lot there. It's a topic where I don't see a lot of papers getting written, but I can tell you that there's a ton of chemical treatments getting pumped by operators all the time, and they're getting a ton of value from it. So a lot's happening below the surface that is not super talked about.
Right. Maybe we'll just end with it. Let's two more. You see this kind of higher density fracturing or refracturing have opportunities for orphan wells, which maybe have a broad definition. I don't know. It's the question, yeah, are there technical pathways being studied so we can turn these wells from being a plugging liability, like plug in a well that's not producing anymore, or for future production. So maybe that's kind of an old well versus new well kind of thing as well. So I'm not sure what you can tell us, or vertical and horizontal, all kinds of stuff. Go ahead.
Yeah. Well, there are many kinds of orphan wells, right? From of many different ages and formations and things. Certainly, an older well that's drilled in a shale play that's a horizontal well is a refrac candidate. Even the Barnett shale wells from 20 years ago, there's some really neat refrac being worked on those wells, which is pretty amazing. Given the right circumstances in the right place, yes, if the resource is there.
All right, I'm gonna ask this one partly because I don't know what this phrase means, so maybe you can tell me. What are your ideas on frac hits mitigation strategies?
Yeah, so frac head means when you have a newer well. So let's say we have a 10-year-old well and we come in later and we drill a neighboring well. That neighboring well is the child well, and the frac hit is when the fractures from the newer well come over and they intersect with the fractures from the older producing well. It is a significant problem. Number one, because the stress change from the prior production tends to attract the fractures. So you get kind of an asymmetrical fracture geometry and you get a less uniform placement of fractures. And unfortunately, fractures tend to grow in the place where there's already been production, which is where you least want them.
Hmm.
Um, and number two, it can mess up the parent well. Like I mentioned, it can cause degradation of production in the parent well from degradation of the proppant pack conductivity. So it's a negative on both the old well and the new well. That's a frac hit. There's no silver bullet on mitigating frac hits. There, to some extent, we have to just engineer around it. Space the wells appropriately, be aware it's going to occur. There are steps that you could take to reduce issues. Small volume preloads, which means you actually stop production and pump some water into the parent well. Those can be helpful for preventing proppant influx into the well and help you avoid needing to do cleanouts, coiled tubing cleanouts. But unless you pump just kind of unrealistically large preloads, you really can't completely mitigate frac hits, unfortunately. It's more about field development planning. And what companies do today is just try to plan where and when they're going to drill the wells to try to have as few of these as possible, kind of over long term, even though you can't avoid it. There's a lot of wells out there, and you're gonna have frac hits.
Right. Okay. Thank you very much. So we'll leave it there. So thank you again. It's been Mark McClure, co-founder and chief executive officer for ResFrac. Thanks for being with us on the UT